Okay, last time I kind of talked about errors at a high level, the whole weakest link in the chain thing. This time I'm going to start working my way through the different flavors of error and maybe try to cover some of the ones that we might be able to quantify or kind of at least attempt to put a number to. So remember, you got this data set, you can do error checking to try to quantify things. You can go out on the surface and you can get a measurement and you can compare that measurement to the number that you have in your data and see how close they are. Different approaches to doing that checking, and I talked about those last time. You also need to remember what type of data it is that you're checking on. If it's nominal and ordinal data, you're not going to be able to get a lot of quantitative numbers in terms of each individual data point. But if it's interval and ratio data, you may be able to get some numbers about each and every point or many of the points individually and how they compare. If you have nominal and ordinal data, the categorical data, you usually use what's called an error matrix to estimate your error. So the way this matrix works is, let's say you go out and you do your checking and you do checking at 76 points. Okay? The rows in this matrix are what really is out there. So when you go out to the 76 points, you go out and you find that really there are 26 urban places. I went out, I checked, I made sure it was urban. There's 26 of those 76. The columns are the classified land cover. Okay? So the bottom total is the classified land cover. So if you look at this, you see that 27 of those spots were classified as urban in the data set. So which ones were classified correctly? The ones that really were urban, that were classified as urban, the ones that really were forest, that were classified as forest, the ones that really were ag, that were classified as ag. So if I add those three up, divide it by the total number of points, that'll give me a measure of the overall accuracy. This accuracy can be split into two pieces. One would be called the producer's accuracy, and that's how good whoever made the data set was at creating that data set. So that's the producer's accuracy. So if we look at the producer, they classified 22 things as urban that really were urban, right? So there's 27 total that were classified as urban, but only 22 of those really were urban. So 81% efficiency. Forest, 19 were classified as forest that really were forest, but there were 25 that total were classified as forest. They made a mistake when they called 4 of them agriculture, and they made another mistake when they called 2 of them urban. So we got 19 over 25. Ag, similar thing, 20 over 24, 83%. So we're taking our diagonal and we're dividing it by the classified total. We also have what's called a user's accuracy, and that's what a user could expect by using this data set, what type of accuracy they could expect to get by using the data set that the producer made. So urban is going to say 22 of those were urban that were classified as urban, but really there were 26 classified as urban. So if I'm using the data set, I'm only going to find 22 in the data set that were classified as urban that really were urban. So the accuracy for that's 85%. And you can see the way this works, it takes the diagonals and it divides them by the real or the row totals. So we have producer's accuracy, user's accuracy. You can combine these producers and users accuracy to get what's called the coefficient, kappa coefficient of agreement. The equation is down here. I won't talk much about that. If you plug and chug the numbers in this example, you see that the kappa comes out at 70%, and in general 40 to 80% kappas indicates moderate agreement. So that's a moderately classified data set. Okay, how do we do numeric data? Numeric data is going to be a little bit easier to do because we're going to be able to use this concept of root mean square error. And we're going to be able to apply this to interval and ratio data. So what is root mean square error? You can work from the back to the front, and you can see that the E stands for error, the difference between what it is on the real world versus what it is in your data. You go to all of those points that you checked, calculate that difference, that's the error. You square each one of those errors, that's the S, square each one of those errors, and you're going to get the squared error. You take the average of all of those, all in this case 74 points or whatever it was in the example. The way you take a mean is you add up all of the squared errors using the summation, divide by the number of points, and you get the square root there. It gives you the root mean square error. So squaring these errors allows you to take into account the fact that maybe some errors are positive and some errors are negative. They would cancel each other out if you didn't square them first. So what you do is you square them first and take the square root. That gives you a better measure of kind of what the error is about. Okay, there's these other error types that you can think about. Attribute logical consistency. Attributes are the whats that are associated with your points, lines, polygons, or raster cells. So when you store those things in your GIS, in your database, you're going to set up some rules. And if the data set followed all the rules when you set that up, it will adhere to the logical consistency. So let's say you have the United States. You'd want every state to have a name. So if every state has a name, it's going to adhere to logical consistency in the name portion of that data set. So it's basically making sure all the T's are crossed and the I's are dotted with your data structure. Spatial and attribute completeness, that's kind of like that logical consistency, but spatial covers everything with the same level of detail. You'll see problems with this sometimes when there are places that are hard to get to and places that are easier to get to. You might have more data in the places that are easier to get to than the ones that are harder to get to. So that becomes a spatial issue. Thematic, you don't have missing values, you don't have things that aren't done. Positional error. Okay, this is another one that you can kind of quantify. This is how close the coordinates are to what they are in the real world. Usually depends on the scale. If you're covering a small area, you're going to probably have lower positional error because you can see much finer pieces of measurement on that small area. So a large map scale is a small area, and so the large map scale is going to have a smaller positional error. This is the topographic map scales 1 to 24,000. That's the map scale. It's a ratio. The next higher up topo map is 1 to 62.5. 1 to 24,000 covers 7.5 minutes of arc. 1 to 62.5 covers 15 minutes of arc. The larger map scale is going to cover a smaller area, and so it's going to have a smaller positional error. How do we report these positional errors? We use what are called accuracy standards. Again, this is people who know what they're talking about, who think about it and say, let's make some standards. If people adhere to the standards, they can just report that they adhere to the standards and they don't have to give us a bunch of numbers about what they do. So these have evolved over time. The older ones were the United States National Map Accuracy Standards. That evolved into the ASPRS standards when we started getting remote sensing and satellite data, and that's evolving into the FGDC national standard, which is NSSDA. And so this FGDC, again, are the people who know the best how things work, and they have the most modern standards for positional error. So what are these accuracy standards? They're based on that root mean square error, both horizontally and vertically for position. If we look at this table of the remote sensing ASPRS standards, we see that there's a variety of scales here. These are all what would be considered large scale maps. So they're going to have smaller areas that they cover, and so they have smaller positional error. So you can see the lower the area that you cover, the larger the map scale, the smaller the error. This is the old standard, the National Map Accuracy Standard, and these standards apply to most of the topo maps that you'll see. So here's a 1 to 24,000 topo map, the 7.5 minute map, and in this block you can see that it says it complies with NMAS standards. Okay? So what are NMAS standards? In this case, they're based upon when the map was made, which is on hard copy paper. And so when they're drawing lines on the hard copy paper, the lines have a certain width to them, and you can't really ever get accuracy closer than the width of a line. And so the positional error assumed on these maps has to do with the publication scale, or what it was like in hard copy. So for this 24K map, 1 inch equals 24,000 inches. 1/50th of an inch, that's assumed to be the line width of a pen that draws these maps. That's 4.17 feet. So that's what your positional accuracy is going to be for a 7.5-minute topo map. If you go to a 15-minute topo map, you're going to get worse positional error, right? Because the width of that pencil is going to cover more land surface. And so what we have there is that 1/50th of an inch becomes 104 feet in the real world. So you have much lower positional error as you go to higher areas that you're covering. How does it work for vertical accuracy? Well, the topo maps, this is one that's easy to remember. Vertical accuracy of a topo map is 1/2 of the contour interval. You go back to this block down here and you see that the contour interval for this particular map is 40 feet. So the vertical accuracy is such that no more than 10% of the elevations on that map are off by more than 20 feet. If we go to a map that has a different contour interval, we're going to have lower positional error. In this case, it's 80 feet. So 80 feet contour interval is going to give us 40-foot vertical positional error. Okay, topological error. I think I'll cover that one on the next video, so we'll stop from there and go into another video to cover the rest of those topological and temporal errors.